Okay, first let me share my screen. Can you see my screen?
I see your PowerPoint.
Yeah, you can see, right?
Yes, we can right now.
Oh, so you can see, right? Yeah, my
Yes,
okay,
yes,
great.
Doctor.
Okay, so as you can see, today I will be discussing the questions and answers to a couple of questions that I have set up. So everybody will participate. So really, this will be an interactive session. Um, so I will be reading the questions and I will be discussing the answers. So you all will be noting down by using pen and paper, and later again I will be writing down the answers, and then I will be posting. Um, everybody see the very first questions. What are the main devices that realize data acquisition or collect signals from various parts of a smart grid network and send those signals to the SCADA system? So, do you understand the question? So, question is, which devices or what are the main devices that capture data acquisition and then or collect signals from various parts of the smart grid? You know that smart grid is huge. There are lots of nodes, buses, lots of measurement location. So what are the main devices that take participate in collecting signals and then send back those signals to the main control system, which is the SCADA? So therefore, you see, the answer would be that RTU. You can write down RTU. RTU means remote terminal unit. You know that before the exam in on class we are discussing, it is called RTU. RTU basically one of the components of SCADA system. So RTU is one component. Second component is PMU, phasor measurement unit. Phasor measurement unit. So RTU, PMU, and write down another thing, various sensors. Various sensors. So therefore, throughout the smart grid network or microgrid network, there are lots of PMU, RTU, and sensors are placed. Those are continuously monitoring the system. They are gathering various data like voltage data, power data, frequency data, reactive power data, speed signals, or any change of system behavior. Those devices are collecting and they are sending to the SCADA. And then SCADA is looking and monitoring and analyzing, evaluating those parameters. And based on the system behavior, the SCADA is making decision what signal and where to send back. And kind of the SCADA is making control decision. So as I said, the appropriate answer main devices are three: PMU, RTU, and various sensors. Does anybody have any questions? Okay. If no, so moving forward, you see question number 2, wide area measurement and control. It is called WAMC. Is an important subject matter for a smart grid system. But is there any drawbacks of that WAMC system? Explain your answer. So you know that wide area measurement and control, what does that mean? You know that smart grid or even conventional power grid is hugely interconnected. For example, in United States, that power grid is highly interconnected. all systems are not located in any specific place. It is scattered, but they are all interconnected. Now, you know that SCADA is the master control center or centralized control system, which is the main decision maker or master decision maker. That's why you have to collect, SCADA needs to collect signal and various measurement for control purposes. That's why it is called the wide area. Wide area means the vast area, very large area, very large network. So now, okay, that WAMC system is measuring and collecting signals and making control decision. But do you think that there could be any drawbacks or limitation of such system? So what do you think?
Yeah, there should be some. It might cause the delay, and it might be more prone to the cyber attack because
Exactly. Exactly. Yes. So because it is wider, so all are not equidistant, or not all systems are not located equal distance from the SCADA. Therefore, while collecting signals, it is highly likely there could be some sort of delay. So therefore, right answer, there should be some delay, and even the hacker or cyber attacker may take chance to attack any control system, any measurement thing. As I mentioned, to answer to question on, they can damage or they can malfunction, misoperate those RTU, PMU, and then sensors. So the appropriate answer is yes. So the drawbacks is that there could be time delay, communication delay, and there might be cyber attacks or cyber hacking at any point of the entire power grid. Okay, so moving forward, you see the question number 3. How can the malfunction of the meters on the high power line affect the control system in a smart grid system? So you see, how can the malfunction of the meters on the high power line? Now, you see, I just mentioned while I was answering to question number 2, it's highly interconnected system. So it is not just like that. It has only the 120 volt or 4.6 kV. So there are high power line which carries very high voltage, and on those high power lines or high voltage line, there are different meters. Like one example of the meters is the frequential meter, like which is called the PT, that measures the high voltage along the high power line. And other one is called the CT.
there is some noise.
Yeah, so someone is talking.
Yeah.
It looks like someone is talking. Anyway, I think now we stopped. So you see that along the high power line, there are two main measurement devices or two main meters. One is called PT or the VT to measure the high voltage or high potential, and other one is called CT, high current measurement. So now those CT and PT are measuring the high voltage and high current, and those voltage and current signals are being sent to the SCADA. Now, if there is any malfunction of the meters, this means if the CT and PT do not measure correctly, then the controller will get wrong signal. Accordingly, controller will behave wrongly, inappropriately, and that will impact the performance of the grid system. So that is the answer. So everybody understands?
Dr. Ali, I have a question.
That
Sure.
the controller will get the wrong signal and will then handle it inappropriately and affect the system in a bad way.
Exactly. So malfunction means those meters are not operating correctly. They are misoperating. And what are those meters? it is called the PT, potential transformer, and CT, current transformer. So it might be surprising to you that a transformer can measure high voltage and high current. You know, in the laboratory, like in electronics laboratory, circuit laboratory, or even in the energy conversion laboratory, you have noticed there are, conventional small size voltmeter and ammeter. So those are suitable for the lab only. But it's the high power line. High power line means voltage is 115 kV, 161 kV, up to 1000 kilovolt. So therefore, you can't use the traditional voltmeter and ammeter which are available in your laboratory. That's why you need transformer. So to measure the high voltage, it is called the potential transformer. To measure the high current, it is called CT, current transformer. So those two are the pretty standard devices, measurement devices, which are placed on the high voltage line or high power line. So if they malfunction, means if they misoperate, then the controller will get inaccurate or wrong signal. And that will adversely impact the smart grid or the power grid system. Is this fine?
Dr.
Okay.
Ali, one question.
Yes.
To measure current and voltage, is there a technique beside the instrument transformer?
No, that is the only thing I used on the high power line.
Okay.
Yes. That is for the high power line. Because,
Yes,
you know, in your laboratory, you have the ammeter and voltmeter. Those are maximum 30 ampere rated or maybe 20 ampere rated. Your voltmeter can measure for single phase 120 volt, for example, in this country. And for three-phase system, line to line, it can measure 208 volt. So laboratory voltmeter or ammeter are rated only to measure voltage in the range of volt and in the range of ammeter, in the range of ampere. While on the high power lines, it is several thousand ampere. And then as I told you, like up to 1000 kV. So that's why the only way to measure the high voltage and high current are the transformers. Yes. Okay, so moving forward, everybody see the next question. Consider the following closed loop control system. I am showing the picture that is in the next slide, where the central control office calculates the total kinetic energy, TKE signal, based on the individual speed information from the power sources. That might, also what is on the right side? I cannot see. Okay, so can there be, there might be any signal and communication delay from the central control office to the fuzzy control block that might affect the power grid performance. Okay, so see the next slide. Okay, everybody see the, can you see the picture, like example of SCADA operation?
Yes, we see it.
Okay. So everybody see at the bottom, like before, I think I showed you this picture, maybe 2 classes back, and the other day we were discussing communication delay. So you see at the bottom, that is the central control office. It is calculating TKE. TKE is that total kinetic energy. And that total kinetic energy signal is required by this fuzzy logic controller. I mean, whatever the control structure is, that fuzzy logic controllers requires TKE signal. Now, you see it is collecting speed signals. There are 10 generators G1 through G10. All are scattered, all are dispersed, all are not located at equal distance with respect to the central control office. Now the question is, while collecting signals, can there be any delay or time delay or communication delay, you think?
Yes, there would be.
Yes, there would be the delay. So therefore, if there is delay and if the amount is significant, for example, several hundred milliseconds, then the TKE calculation will be delayed, significantly delayed. Consequently, the fuzzy controller will receive delayed signal. It will produce delayed output. So finally, the impact will be delayed. So the system will not behave appropriately. There might be some fluctuations in voltage, current, or the frequency. So that's the answer. So again, I'm moving back to the previous slide. So that was the question. Can there be any signal or communication delay from the central control office? And if so, how it affect the grid performance? Okay, then another question number 5, everybody see. In case of a conventional power network consisting of synchronous generator, so the total kinetic energy information is used as a global variable to evaluate the transient stability of the system. So for example, I mean, just now we showed this picture, you see, that all 10 generators, G1, G2, G10, those are the conventional system. Conventional generator means those are the synchronous generators. And still, you know, those generators are widely used all over the world. So, and then because those are the synchronous generator, so speed signal is the main variable. And that speed signal creates the total kinetic energy. So that's why the total kinetic energy is a very popular or the global variable in case of the conventional system. And you keep in mind that in this system, all generators are synchronous. There are no wind generators, no photovoltaic or other system. So that's why we use the total kinetic energy. Now the question was, now come back to the question 5. In case of conventional power network that consists of synchronous generator, total kinetic energy information is used as a global variable to evaluate the transient stability performance of the system. But a microgrid has variety of power sources. Now see the power grid in slide number 3. So I am going there, so let's finish the question. Then how can we evaluate the transient stability of the microgrid? Or in other words, in case of microgrid that has variety of power sources, not just the synchronous machine, likewise the problem 4. So in that case, what should be the global variable that should be captured or that should be measured by the SCADA? And then that will help you evaluate the stability of the microgrid. So now everybody see slide number 3. Yes, everybody see this picture. On top, I have written SCADA. And what are the sources? You see the DFIG, this one is like wind farm or wind plant. Next, you can see this is the solar farm. And then there is on supercapacitor energy storage. And then right side on top, you see SG is written. That is the conventional system, synchronous generator. And then there is line, and then that is connected to the 11 kV grid. So this is the main power grid. And you can see there is a control device which is called TSC, thyristor switch capacitor. This is a controller for this system. Now everybody say like that wind farm is producing 0.6 kV and then on the secondary side of transformer 11 kV, and that is attached to this common bus. This is the common AC bus, this board line that has 11 kV. Solar is also producing 11 kV with the help of transformer, and energy storage left side is 4.16 and 11 kV. So therefore this is the main bus, and that bus is also connected to that conventional system. So now for this system, you see on top there is SCADA. What do you think, what should be the global variable in this case? In this case, still you will collect the speed signal from the generators, and then you will make total kinetic energy, likewise the previous case, or there is any issue in getting the speed signal to the SCADA. Do you understand the questions? Because this is example of the microgrid, it has variety of different sources. There is conventional source, synchronous generator. There are wind, there is solar, energy storage, and the main grid. So Bharan, all power sources are not synchronous. Like there is wind, there is solar. So what do you think? What should be the global variable?
Maybe some phasor information.
Yes, of course. But phasor information might be a little bit difficult. So what you can see in this bus, you see in this bar, what information is easily available in this bar?
Voltage.
Voltage, exactly. Absolutely right. So therefore, in this case, what you can do, because all voltage are appear here, so you can collect the voltage signal. This means in this case, you can say, I will collect total voltage information, and that signal will go to SCADA. That's why, I mean, everybody keep in mind, in case of microgrid, like voltage, total voltage, that information is most dominating, most helpful to make a decision by the SCADA. So therefore now you got the answer. So now come back to question number 5. It was the question, but a microgrid has variety of power sources. Then how can you evaluate the transient stability? So the answer would be, because there are variety of power sources, so we will be collecting voltage signal from the terminal of various power sources, and then it will be summed up at the SCADA. And that global variable, this means total voltage information, will be used to evaluate or to assess the transient stability performance of the microgrid. Is everybody fine?
Yes.
Okay,
I only have a question.
sure.
So if we use the voltage for SCADA, that means the feedback for synchronous generator should be different, right? Because we are using voltage instead of speed.
Right. So therefore, from synchronous generator also, we will measure the voltage from its terminal.
So our SCADA for synchronous generator should be different, right? Shouldn't be the same as the previous slide.
Yeah, right, exactly, yeah. No, I mean, no, I mean, from the synchronous machine, it is separately collecting the speed signal. But that speed signal, SCADA is just keeping it just for local control of that synchronous. But that speed signal is not being used as a global variable. As a global, by the global, I mean a common signal.
Yes.
So therefore, from the synchronous generator, definitely it is producing voltage, right? It is producing voltage. So in addition to the speed signal, the voltage signal is also going to the SCADA. But as a global variable, SCADA is just making some of the voltage signal only from all sources, because every sources has voltage. You know, the wind generator has speed. There is no issue. But you know, does photovoltaic has any speed? No,
No.
because photovoltaic is static. What is that? Supercapacitor energy storage is static.
Yes.
Even like I did not show the fuel cell. Fuel cell is also a static device. So that's why that question is coming. In a microgrid, you cannot use the speed signal or the kinetic energy as a global variable. But of course, that speed signal and frequency signal is being exchanged or being sent to the SCADA.
Excuse me, sir.
Yes.
Sir, what do you mean by speed signal? Like, is it a voltage or current or something else?
No. Speed signal means the speed of the rotor from the moving.
Okay, only the speed of the rotor.
Yeah. Because in the previous problem, in the previous question number 4, it was the issue with calculating kinetic energy. So kinetic energy, you know, half mv square.
Yeah,
So,
yes.
you know the velocity or the speed information. And mass information you will be getting from the manufacturer, nameplate, or at the SCADA that is available. But now, question number 5, we are talking that it is microgrid, and microgrid has different sources, not just synchronous machine. So it has solar, wind, and other source. That's why you cannot use speed signal or the kinetic energy as a global variable.
So we are using the rotor speed to calculate the total kinetic energy, right?
Yeah. That was the previous question. Question number 4.
Yes. Yes, sir, I got it. Thank you.
Yeah. This is very, very vital. I mean, for example, if anybody does research in power area or microgrid area, like whatever in the university or in any power industry, this is very, very important. I mean, question number 5, what signal you will be using in a controller? So at that time, you will be to know the voltage is the appropriate signal for microgrid.
Dr. Ali,
Yes.
why we don't consider the current state of voltage?
You can, but you know that at that bus, you see that system once again, the current from different sources might be different. You see that they are connected in parallel.
Yes.
So depending on the capacity, they might contribute different current, but it is a common bus. Common bus means voltage is the same. That's why voltage is used instead of the current. I mean, you can use current. There is no issue technically, but you have to measure the current from the various sources, and current value is not a common variable. Again, there might be load in the system that might draw different current. That's why it is appropriate to use a global variable, in this case, this voltage information. What voltage is available here? A common voltage. That's
Okay.
all. Yeah. But I mean, if someone decide, no, I will be calculating current, I will be taking the measurement of current from each, they can do it. It will also work. But in a grid system, always like voltage is used, because that common voltage, you see 11 kV, 11 kV, 11 kV. So it is easy to use the voltage signal.
And also it will be costly, right? Because we need to
Yeah.
have a lot of measurement for current.
Exactly. Yeah. Okay, so then moving forward. So everybody say now question number 6. What is the range of communication delay in a power grid? So what we learned in the communication delay just before the exam, that previous class. What is the range of delay?
So it's few hundred millisecond, maybe up to 200-300.
When I'm saying the range, I mean from where to where. So like the answer would be, okay, from microsecond to several hundred millisecond. It can be several microsecond to several hundred millisecond. That is the range of the communication delay in a power grid. So whatever the system is, even the very fast system, still there would be some sort of delay. And that delay, at least it could be 50 microsecond, 100 microsecond, etc. Like I was showing the picture of the GPS, global positioning system. It has like 1 microsecond, 2 microsecond delay. I mean, that is negligible, but still that has delay. Now, because we are talking about the power grid, it's not just the GPS. There are lots of, I mean, it's a hugely highly interconnected system. There are lots of control system, lots of devices, voltage regulator, governor, AVR, etc. So all are like introducing microsecond delay, and then the total delay is several hundred to several hundred milliseconds. Okay, and then consider the SCADA of a smart grid delays about 1.2 seconds to send a required signal to a controller. Does this amount of delay have any impact on the controller performance?
Yes, this is a huge delay.
Yes. So like I made a number 1.2 seconds. This is huge, because just I said that the range could be up to several milliseconds. You know, before the exam, in the previous class, I showed you result in one of my simulation cases, that if the delay goes beyond 500 milliseconds, systems fully upset, system fully collapses down. So that's why 1.2 seconds, it's too big with respect to the modern grid or the current grid. So that's why definitely there will be significant amount of delay to the controller, and then that controller will degrade the performance. And then that degrading performance will go on the entire grid or the entire system. So is everybody fine so far?
Sir, can you repeat the third
Yes.
question?
The question number 6.
3.
Oh, 3.
Yes,
Okay.
sir.
So question number 3 was, how can the malfunction of the meters on the high power line affect the control system in a smart grid? So first question on the high power line. So what are the meters? So there are 2 important meters. One is called potential transformer, PT, which measures high voltage, and other one is called like CT, current transformer, that measures high current. But I am asking that how can the malfunction? This means I'm assuming that somehow those meters are not functioning properly. They are giving wrong reading or the wrong result. And if the wrong reading or wrong result goes to the control system, controller will produce the wrong decision or wrong information, and that will affect the performance of the entire smart grid system. Is this fine?
Yes, sir.
Okay. So as I told you, like again, I myself will be writing down all the answers and then I'll be posting for you. So now, and I mean, because it is interactive session, like you all are participating, so I would recommend you, it's kind of the brain work. Everybody think the answer, and then based on my answer, you note down, and then again, I will be posting the answer. Then you see your note and then you correct it. But everybody now, I mean, think carefully. This is very important and very critical questions. So everybody should understand and need to understand. Okay, so moving forward, now this is second, this is third slide. Okay, here is the question number 7. You see, question number 7 states, the following figures depict the voltage and frequency control of a microgrid while shared by the wind generators through Drupe characteristic. So this means figure 1 and figure 2 are showing the frequency Drupe characteristics and voltage Drupe characteristics. Okay, so first let's finish the question. Consider there is a charging station in that microgrid system. Now, figure 1, figure 2 are the frequency and Drupe characteristics, and assume that there is a microgrid, and in that microgrid there is a car charging station. So the question is, will the charging of many cars simultaneously affect the power quality of the microgrid? Now, first of all, power quality means 2 parameters, frequency and voltage. So, I mean, I think except Amanish, none of you have joined my power quality class. The definition of power quality is ensuring the frequency and voltage, meaning that the controlling frequency and voltage, that is the meaning of power quality. So the question is, will the charging of many cars simultaneously affect the power quality? So the what is the answer?
Yes, it does.
Yes, because many cars are being charged simultaneously. So now see this one. Now everybody see figure on. What does it say? Frequency here F naught and corresponding active power. Oh, so P stands for active power or real power. In figure 2, symbol Q stands for reactive power and F stands for frequency. So you see the pattern, this is like decreasing. That's why it is called the Drupe characteristics. This means with the increase of the active power or real power, frequency will degrade or frequency will drop, and that makes sense. For example, now you have 60 Hertz. So if you insert more and more load on the system will slow down. Consequently, frequency will drop. So that's why what is happening. This means if you insert more and more active power in the system, frequency will change. So the question was, will the charging of many cars simultaneously affect the power quality? So the answer is yes. And when I'm asking explain your answer, explanation is that the figure on shows the frequency Drupe characteristics. So while you are charging cars, this means car is drawing huge real power. because there are many cars. So it is drawing the real power. So consequently, frequency will drop. Then now based on the right side figure, voltage drop, you see, if the reactive power gradually increase, then the voltage will down. So in other words, because you are charging many cars simultaneously, so certainly there will be some voltage drop. And that voltage drop will cause high reactive power. And what is the impact of the high reactive power? Impact of the high reactive power is low power factor. So this means the system will be lossy as well. So that's why the question, will the charging of many cars simultaneously affect the power quality? So the answer is yes. You will be telling that because many cars are simultaneously being charged, they are drawing high power. And that high power means high real power or high active power. That will cause the frequency down simultaneously because many cars are being charged, so voltage will go down. Consequently, the reactive power will increase, and that will impact the power quality because the power factor will be low. So that is the answer. So is everybody fine?
Yes.
This is also very vital, very important questions that I have brought here. Okay, now you see that today I think I have set up 15 questions. So again, like we have done about 50%, so another 8 questions are remaining for you. Because you know that for this course, there is no specific textbook or book. That's why I have set up the questions such that these questions serve as the textbook for you. So I am helping you there. Okay, everybody please read the number 8. To smooth out the intermittent performance of renewable energy sources in a smart grid system, will the local storage or the distributed storage capability be needed? You know, the renewable energy sources means solar energy, wind energy, ocean energy. Now you know that these offer intermittent performance. Intermittent means because solar performance is dependent on the sun intensity or solar irradiance, but that is changing. That's why it is called intermittent. Similarly, in case of the wind generator, wind speed is changing or varying. So that's why they are offering or they are exhibiting intermittent performance. Now, to solve this problem, do you think the local storage, local energy storage, or the distributed energy storage capability be needed? So local storage means, for example, you have a solar system, then you attach a energy storage with it. You have a different system like wind generator, and you need an energy storage to be connected at its terminal. So those are called the local. But think that smart grid is highly interconnected system. It's huge. I mean, already I showed you the picture. So the distributed storage means in addition to those local storage which are installed for each and every energy source, time to time along the lines, there are other storage as well. Those are called the distributed storage. So the question was, will only the local storage or the distributed storage capability be needed? So what do you think?
I think both.
Both, exactly. So the perfect answer. So the answer would be both local storage as well as the distributed storage capability will be needed to handle or to tackle with the intermittent nature of the renewable energy sources. So please write down the answer that both local energy storage and the distributed energy storage will be needed to handle or to cope up with the intermittent performance of renewable energy sources.
I have a question.
Sure.
So, I mean, the battery that is installed locally in the renewable energy storage, I think that alone should be able to deal with those intermittents, right? Those, I mean,
No. So typically, the battery system that you are talking, for example, if you now purchase a solar system, it comes with the battery. It is there. You don't need to tell them about battery. If you purchase solar system, they will give you a battery. That battery is just for the nighttime use. During daytime, with the excess power, it will be charged, and at night time or at cloudy moment, it will deliver power. That battery does not have the capability to handle with the fluctuations of frequency, voltage, and power that is coming from the irradiance or solar change. So when we are talking about the storage, like battery energy storage, not just the battery. So storage system, you will be assuming that in addition to that battery or whatever it is, supercapacitor or SMS system, in addition to that battery or coil or capacitor, there is DC to DC converter, there is DC link, there is voltage source converter. It has the control capability that can maintain or suppress or mitigate the frequency, power, and voltage fluctuations. Do you understand?
Okay.
Yeah, that's why, okay, the local storage means that can handle only that local, but once it is going, for example, you have one one photovoltaic system or wind system, you have that battery energy storage. Okay, it is smoothing the power. But once it is going at the common grid point, because at the common grid point, other sources are also connected. When you will be collecting all signal, then there might be some sort of oscillation that you have to suppress as well. That's why along the common bus, like I was showing in another figure where you are measuring the voltage, along the common bus also you need or you should put energy storage. Those are, I am telling, the distributed storage system. For example, that common bus or common line is huge, 100 mile. So you might need couple of or the several distributed storage. But of course, you're right, each and every power source has its local energy storage system. But we are talking in addition to that local storage, you must need still the distributed storage to properly suppress the fluctuations. Is it fine?
Yes.
Okay. Now everybody please read question number 9. This is kind of the quiz for you. For the purpose of power factor improvement in a smart grid system, which of the following devices or device would you choose? Explain.
Capacitor.
Sorry?
It's a capacitor, right?
Yes, that is right. And the students who have attended energy conversion, what's your answer? Answer from the energy conversion viewpoint. Can you pick up any other device?
Synchronous motor.
Exactly. So I want to hear from someone who attended energy conversion, like Uthman.
Yes, synchronous motor.
Yes. I think everybody, who attended energy will agree. Synchronous motor, it is called the synchronous condenser. When it was overexcited mode, when it is overexcited and there is no load in the system, that time synchronous motor works perfectly as a capacitor. That's why the synchronous motor, when its name is synchronous condenser, please everybody write down the name, synchronous condenser, CONDENSER, synchronous condenser. When motor has no load or very little load and it works in overexcitation mode, that time, or in the leading power factor mode, that time it behaves perfectly as a capacitor. So in other words, synchronous motor has the capability to work as a capacitor. So that's why the Manoj, so your answer capacitor is right. And then also, like everybody is telling, synchronous motor. So the appropriate answer is yes, synchronous motor and capacitor.
So,
Yes.
excuse me.
Yes.
Yeah. So you're telling about that overexcitement mode,
Yeah.
where the power factor is positive.
Leading, power factor is leading.
Yeah, I mean, yeah, leading power factor.
Yeah.
So in that case, so it is acting as the condenser. Okay, I mean.
Yeah. I mean,
Capacitor, right?
I mean, when it acts as a overexcited mode, what happens? The angle between voltage and current across the motor becomes like 90 degree.
Okay.
So this means the current leads voltage by 90 degree.
Mm-hmm.
Current leads 90. This means it behaves as a capacitor. And
How?
at that time, because it is providing leading power factor, because
Okay.
if you know that first you chose the capacitor number 4, because
Okay.
the capacitor can provide a leading reactive power factor.
Right. Yeah.
Inductor can provide reactive power, but that is lagging.
Mm-hmm.
So the capacitor,
Yep.
same thing. I mean, synchronous motor under a certain condition. What's the condition? When it is overexcited mode, when the current leads voltage by 90 degree, and other condition, there is almost no mechanical load connected. Just you are running a motor. Like, similar to that, like like the flywheel storage system. It is just running. It is not running any pull or pump, or it is not doing anything. Synchronous motor is just running. I mean, of course, you can argue that there is some loss. There is loss because it's motor. On the other hand, capacitor is a static device. There is pros and cons, but still it works fine as a power factor improvement purpose.
Sir, synchronous motor, we are running it in overexcited mode, right?
Yeah, overexcited modes, and it should not have any mechanical load, or there can be very, very little load connected to it.
Yeah, yes.
Under these two conditions, it appears that the current leads voltage by 90 degree. This means its behavior, its characteristics becomes fully similar to capacitor.
Yeah, yes.
It can provide the leading power factor, or in other words, it is used to improve the power factor.
Yes, sir. Thank you.
Yes, this is very vital. I mean, so you might be asked this question in your job market, job interview. This is very vital, very quick. And then you know that 3 resistor can only consume power. So it does not have any ability to control any reactive power. Resistor, you know, it is happy with the power consumption only. It can consume. So you can say it can little bit control the active power, but it cannot control any power factor or the reactive power. So it has no role in improving the power factor. Similarly, the first one, you know, the DC motor. So it does not, because DC motor is DC, so it is not related to power factor. You know, in case of DC, there is no question of any reactive power. So there is no question at all about any power factor. So that's why you must not choose the DC motor. Okay, so moving forward, everybody read question number 10. The fault type in a smart grid system is uncertain. Then how do you design an intelligent control system for the smart grid? Will you design different controller for different types of fault? Okay. What is the context or the meaning of this question? Read the very first sentence. Fault type in a smart grid is uncertain. This means that fault can be 3-phase to ground fault. For a 3-phase system, it might happen that all 3 phases have been sorted out. For example, in a stormy day, or as an engineer, you are working and you created the short circuit. So that is 3-phase short circuit. Or you created a short between 2 phases. Or it happened that, okay, in a stormy day, a tree has fallen and that is touching only 1 phase, not all 3 phases. Or it touched 2 phases, and then branch of the trees are, you know, attached with those cables, but tree is not fully uprooted, its root is on the ground. That is called like line to ground fault or double line to ground fault. So in that way, there are different types of fault. And I have said that is uncertain. You don't know, is it 3-phase short circuit, or it is 2-phase, or it is only 1-phase. Now, then I said, then how do you design an intelligent controller for the smart grid? Will you design different controllers for different? So I am asking this question because when it is 3-phase to ground fault or 3-phase short circuit, that is the severest case. That time current magnitude is very high and voltage becomes very low because it is short circuit. So that time one type of controller will work fine. On the other hand, okay, it is not 3-phase short circuit, just it is 2-phase short circuit. In that case, short circuit current magnitude is lower. Similarly, voltage is not fully zero, it has some. So at that time, if you can design another controller, that will work fine for the system. On the other hand, if it is like only 1-phase, as I said, the tree, that is like most common, tree has fallen and tree is attaching to that only 1-phase or 1 cable, and then other end of the tree is still on the ground. So in that case, the current magnitude is not that high, even voltage does not go below that much. So in that case, another controller or different controller will work fine. So now the question is, because the fault type in a smart grid will be uncertain, so how will you design an intelligent controller, Nikon? Will you be ready with different controllers, or can you make only one controller? Is there any way? Because I mean, of course, I mean, you can argue that if I design different controllers based on different types of fault, then the performance will be much better. But that will be like too costly because you need lots of controllers. That's why you should design only one controller that can handle all type of faults. So now the question is, when you are designing a controller, only one controller, how will you design that one? So the answer is that you have to consider the severest case, severest situation. What is that severest situation? That 3-phase to ground fault or 3-phase short circuit. You will be taking the voltage and current reading of that severest situation. I mean that 3-phase short circuit or 3-phase to ground. And based on that, you design your controller and you put it, install it on the system. Now when the it is 2-phase to ground fault or short between 2-phase or only fault in one line, the same controller will work. On the other hand, if you say that no, then I will be designing, because only one controller, I will be designing, assume that only there will be fault, only 1-phase. Okay, you can design, you can make that argument, but if you put only one controller, assuming that it will be only 1-phase fault, but that, as I said on the first line, fault is uncertain. The day when it will be 3-phase short circuit fault, that time your controller will fail. Do you understand? That's why the answer is, instead of designing different controllers for different types of faults, I will be designing only one controller based on the severest situation, based on the severest case or severest scenario. And then I will be installing on the line. So this means that can handle the severe situation as well as all less severe situation. Is this fine?
Dr. Ali, I have a question.
Sure.
We have, for example, 1-phase ground or maybe 2-phase short. Will the electricity run through the line that doesn't have fault or no?
Yeah, so that might flow.
So we only disconnect the line that have the fault, right?
Yeah. So in fact, there will be like circuit breakers or protective relay along the line. So those will trigger, those will operate. So those will, but because protective relay and circuit breaker has some time delay.
Yes.
It is not like immediate. Yes. So we are talking about when you are this type of fault, short circuit, before opening the breaker.
Okay.
Yeah. Very precise type of controller. That's why it is called the intelligent controller.
Okay. Thank you.
Okay.
So Dr. Ali.
Yes.
So talking about the question number 10.
Yes.
So you told us like we have two options. We can design a controller that could work for the worst case scenario, and based on that scenario, other fault condition would be taken care of.
Right.
And other is like, distributed controller, design different controller, right?
Yeah. Right.
So can't we design a single controller,
Yeah.
which control function would be based on different scenario or fault?
Yeah, that is the thing I told. The thing is that you can, for example, you took a common controller, and you want to track with the help of sensor, with the help of measurement, you can distinguish different controllers.
Right.
But you need different types of parameters. Now, when I'm saying intelligent controller, that can be fuzzy logic controller, that can be any proportional integral controller, and whatever the type of controller, there is some sort of parameter that you need to tune. So
Right.
therefore, you can make one single controller, but because you want to optimize for every controller that you are telling, so you have to be ready with separate type of parameters. That will be somewhat difficult
Costly.
and that will be costly. Right?
Okay, I got it. Thanks.
That's why, in real practice, what is done, system is designed, controller is designed based on the severest case or the worst case scenario. So this means you have one set of parameters, and then because it is uncertain type of the fault, so whatever the type of the fault, but your system is, your parameters are set for the worst condition, the least condition will be handled or taken care of.
Okay.
But of course, you are right. If you put different, then performance will be the best. Yeah, but that will be costly. That's why, in order to avoid the high cost and high complexity in the control, only the worst case scenario is considered.
Okay, doctor. Thank you.
Okay. Yeah. So moving forward, the question number 11. So, like you all studied, SMS is a very expensive device because there is liquid helium, nitrogen, refrigeration system, etc. Then what is the main motivation behind its wider applications in electric power and energy system? But you see, you will see like that day, Layth, Hassan, they were presenting this SMS system somewhat, and they all said, okay, it has a lot of application. So what is the motivation then? Despite the fact that it is very expensive. So the motivation is very short time. Its power handling capability. It can handle the megajoule and then megawatt range of power within a very short time. This means its performance, its response is very fast. That is the motivation only, even though it has the very high expense. So you know that coming back to that point, every energy storage system maintain that charge and discharge, but the SMS system is the fastest so far, and that is the main motivation. Okay, so question number 12. What might be the input and output variables of a controller to charge and discharge a capacitor energy storage aiming at the power smoothing of a photovoltaic power generation system? Explain your answer. So in this case, I am just asking, okay, you want to put a capacitor energy storage with the photovoltaic system because your goal or your aim is to provide smooth power. So, and because you need charge and discharge and you need appropriate controller, what should be the input variable and what should be the output variable? So, because the charge and discharge happens based on the power system requirement. So, because photovoltaic system, due to its solar irradiance variation, it produces varying power or the fluctuated power, but the customer wants a constant power. So that's why power is one of the important input that you have to consider. So the answer is, during charging and discharging, input variable should be the power, line power, that you will be looking. And what will be the output variable? Because you know that charge and discharge, in addition to that supercapacitor, or in case of the coil storage, or in case of the battery storage, in addition to that capacitor or battery or the coil, you have DC to DC converter. So you have to control that DC to DC converter. And that DC to DC converter principle is dependent on controlling its duty cycle. So the output, as an output variable, you have to choose the duty cycle of DC to DC converter. So therefore, everybody please write down the output variables will be duty cycle of the DC to DC converter, and the input variable should be the power, in fact the active power or real power. So this means that your input power is varying, that is coming from the photovoltaic system. Your controller has fixed power, which is the demand or which is the requirement of the customers. So your controller will look the measured power, and then based on the power, it will create an appropriate duty cycle to maintain the charge and discharge. Then the voltage source and transformer, finally it is connected to the grid. So main thing is choosing the appropriate input variable and then the output variable.
Would it be same for the wind energy?
Yes, exactly the same. And then same thing true for the superconducting magnetic energy storage and the battery energy storage. Same conclusion.
Okay.
Okay, so moving forward, question number 13. What are the main variables captured by smart grid monitoring? And how does smart grid monitoring help maintain power quality of the network? So smart grid monitoring means that, like SCADA system, it is continuously monitoring the overall status of the system. So what are the main variables you think that are being captured by that monitoring system? What variables?
Frequency, power,
Frequency, voltage current, active power,
and the phase.
phase, reactive power, power factor. Those are the main variables. So therefore, please everybody write down the main variables that are captured by smart grid monitoring are voltage, current, power, active power, reactive power, power factor, phase, and frequency. So voltage, current, active power, reactive power, power factor, and frequency, as well as the phase. Those are the main variables. And then the next part, like SCADA is monitoring the status. Smart grid has already the steady state operation, healthy condition values of those parameters. If there is any change, then SCADA is making decision, and then that control command or the decision is being sent to the appropriate controller or location to maintain the power quality. In that way, smart grid monitoring is helping maintain the power quality. This smart grid is kind of the government main decision maker. It is getting all signals and it is producing required signal and sending the command or decision to various controllers. And in that way, it is helping maintain the power quality and stability of the overall network. Is this fine?
Yes.
Can you repeat how the smart grid monitoring helps maintain power quality?
Sorry, what is the question?
The answer to how does smart grid monitoring help maintain power quality?
So that SCADA system, when it is monitoring the status of those main variables, now SCADA system has already those predefined values or the steady state values or the balanced or healthy condition values. Now with the monitoring, SCADA system is looking if there is any difference or change in those parameters with respect to the steady state. And if there is any change, then there are different types of voltage controller, power factor controller, or different type of the measurement controller placed throughout the network. The various signals or control decisions are being sent, and those controllers are working and helping maintain the power quality. That's the answer. So the first part question, what are the variables? Just you need to tell name of the variables. Second part, how does it? So this means that it is just watching. It is comparing with the previously said values or the reference values of those variables. And if there is any change or discrepancy, then the SCADA is making some decision and sending the decision to various controllers placed throughout the network. And in that way, it is maintaining power quality. Is this fine? Who asked that question? I think Robert Hampton.
Yeah, I'm fine.
Okay. Okay. Now the number 14, everybody read. How will the stability of an induction machine-based wind generation system connected to a smart grid be affected due to a fault in the grid or due to generation input variation? Assume during the fault, power generation input is constant, and also during generation input variation, there is no fault in the grid. You see, it's like complicated question, so everybody understand fast. You have a smart grid or microgrid system. In that system, you have an induction machine-based wind generator. It is not synchronous machine. It is induction machine. Now, I am asking, how will the stability be affected due to a fault in the grid or due to generation input variation? Now, what I am asking, consider two scenarios, consider two situations. In one situation, there is a fault in the grid. Fault means that short circuit. It can be 3-phase, 2-phase, single phase that we discussed. Or it might happen that generation input variation, because this is wind generator. So there is huge variation of wind speed. And then what I am telling, I mean, these two scenarios are not happening simultaneously. This means when there is fault, then I am assuming there is constant input variation. It may happen that, okay, for 2 minutes, 3 minutes, or a couple of seconds, there is no wind speed variation. So when there is no wind speed variation, at that time, I am assuming that there is a fault. On the other hand, I am assuming that there is no fault in the system, but there is wider input variation. So in both cases, how will the stability of the wind generation system be affected? So the answer is, for example, assume that the generation input is constant. Everybody assume that, for example, wind speed is constant for a certain time, 1 minute, 2 minutes, 10 minutes, whatever it is, or a couple of seconds. So input, generation input is constant, wind speed is constant means it was providing constant power, voltage, frequency, everything was fine. Under that condition, suddenly the fault happened. So what will happen? So this means, because this is induction machine-based wind generator, so write down, voltage will go down, active power will go down, but the frequency and the speed will go high. So write down that when there is input generation constant and fault happens in the grid, write down the answer that voltage will go down, active power will go down, but frequency and speed will go high. That is the impact. Now, come back to the second scenario. There is no fault. There is no short circuit, no open circuit, nothing happened. But I am assuming that continuously input is varying. So in that case, what will happen? I mean, voltage, active power will not go down. Frequency and speed will not go high, but there will be continuous fluctuation. So write down the answer. When there is no fault, but there is input variation, write down the answer that voltage, power, frequency, everything will be fluctuating. That's the answer. Everybody, could you follow me? Number 14.
Dr. Ali,
Yes.
during no fault and input variation, speed will also vary, right?
Yes. Everything will be fluctuating. Torque, power, speed, frequency, voltage, active power, everything will be fluctuating.
Okay.
But the system will not collapse down. Just
Yes.
it will fluctuating. On the other hand, even though the input might be constant, wind speed might be constant, but there is on the fault in the system that is very severe. So in that case, voltage will go down, active power will go down, frequency and speed will go high. And it might happen depending on the system, depending on the capacity of the wind generator, system might be fully collapsed or might be fully unstable. So that's why I'm in two different scenarios. Now, unfortunately, it might happen that, okay, there is a fault and there is wind speed variation simultaneously. That is the most dangerous situation. It might happen in rare cases. In that case, okay, there will be huge fluctuation and also system might be fully upset. System might be fully unstable. So everybody is fine?
I have a question.
Okay.
So you mean, so you're mentioning about the fault, right? So there is a fault in the system. So, I mean, is it inside the generation system or is it somewhere else in the smart grid? I'm talking about the fault.
So talking about the fault, mostly it happens on the line. I mean, for example, you have the wind generator and then it is connected to either distribution grid or transmission grid. I'm assuming the fault on the grid, distribution line or transmission line on the network side.
Okay.
But of course, as you are telling, there might be some short circuit inside the generator itself. For example, coil might be shorted. Then of course, in that case, that situation is more dangerous. Of course, if there is short circuit among the coils inside the generator, immediately there will be short circuit. So voltage will be zero. That is the most dangerous thing. But in this question, by the fault, I mentioned due to a fall in the grid, I assume that it is not it's inside the wind generator. It is somewhere in the grid, mainly on the distribution grid or transmission line grid.
Okay. So what about the synchronous machine based power generation system? Is it going to be the same or?
And you see that if it is synchronous, if it is synchronous machine based wind generator system, if it is wind generator system, still the conclusion is the same. But if it is like traditional power grid, in the traditional power grid, typically there is no input variation.
Right.
That's why the question is regarding wind generation or solar system. So these questions are valid for only renewable sources.
Okay.
And now you can argue that, okay, there has been something in the traditional system, synchronous machine, properly gas is not flowing, there is some change. That might happen only because of some mechanical fault. That is not any natural fault. But in this case, we are assuming the natural wind speed variation or natural solar irradiance variation.
Okay.
Okay, then for today's last questions, can a DC machine be used as a wind generator? What do you think? I mean, what is the context of this question? Like always, I am telling that wind generator is based on induction machine mostly, or just now, like Manoj mentioned, it can be synchronous machine based. But I am asking, can a DC machine be used? Is there any wrong in using the DC machine?
No, we cannot use it, Dr. Ali.
Sorry, what?
I think we cannot use the DC machine.
I mean, it is not used traditionally because DC machine has like traditionally lower capacity. I mean, it can produce low voltage and its power rating is small, but there is no technical issue in using it as a wind generator. So what will happen? It will produce low voltage and then low power, but it will directly produce the DC voltage.
All right.
Yes, and then because it will be based on wind speed variation, so there will be huge variation on the DC voltage and DC power. You can connect a huge size of capacitor to reduce those ripple or fluctuation, and then you connect that to an inverter, and with the help of transformer, you can connect to a grid. So therefore, the answer is yes, it can be used, but for a small application, you can say yes, the DC machine can be used as wind generator, but for a small scale application, because it will produce small voltage and small power. And that is the reason, not only about the wind generator, for traditional system, DC machine is not used. That high capacity synchronous machine is used because of only limitation that DC machine can be applicable for a small scale application or small scale cases.
Dr. Ali, when you say small applications, can you give an example, please?
For example, you can use only at your home, at your office, a wind generator. I mean, not for commercial application. You may have on DC machine,
Yes.
and you may have wind turbine connected. It will produce voltage and power.
Okay.
You can put on your backyard. Yeah, that is the small scale. I mean, the small office or it is not for like grid connection purpose.
Yes.
Yeah. And that is the motivation, to go with the AC machine and not just the DC machine. So is everybody fine?
Sir, can you please
Pitch.
repeat the eighth one? Eighth
Sorry?
question. Can you please repeat the eighth question?
Question number 8.
Yes, sir.
So question number 8 was to smooth out the intermittent performance of renewable energy sources will the local storage or distributed? So the answer will be like both storage capability be needed, both local storage and then distributed storage. So local storage will be handling the local oscillations of the generation sources, whatever it is wind or the solar. And then the distributed storage will further maintain the fluctuation or the stability of the system. It will reduce the further ripple that even might come out from each of those individual sources or the local sources. So distributed storage means those are placed at the scattered locations throughout the network. Local storage means which are placed at each and every generation sources. So that's why to smooth out the intermittent response of renewable sources, you must need both local storage as well as the distributed storage capability.
Sir, local storage means the small generation units, like you mean like substations?
No, I mean, for example, you have a solar system.
Yeah.
Individual. Before connecting to the grid, you need an energy storage there. That is the local storage. Or you have a wind generator. Whatever you connected to the grid or not, you need an energy storage. That is the local storage.
Okay. Yeah.
And then even with those local storage, you connect it to the grid system. On the grid point, on the common bus point, or the point of coupling point, still there might be some sort of fluctuation. You have to suppress those fluctuations. That's why you need the distributed storage capability.
Okay. Yes,
So
sir.
therefore,
Thank you.
distributed storage on the grid level, local storage is together with the power plant or with the internal sources.
Yes, sir. Thank you.
Okay. Any other questions, comments?
Could you repeat the answer to question 1, please?
Question on. Okay. Okay. So the main devices that realize data acquisition or collect signals are RTU, Remote Terminal Unit, RTU, and PMU, Phasor Measurement Unit, and also various sensors. So 3 main devices. But as I mentioned, I think in on class, there is a difference between PMU and RTU. RTU can measure only the magnitude, for example, only voltage or current. But PMU can measure both magnitude as well as phase. So in that sense, at these days, the PMU has been popular over the RTU, but still RTU exists in the system. So therefore, the appropriate answer would be main devices are RTU, PMU, and various sensor. Is this fine?
Can you repeat what RTU and PMU stand for?
RTU is Remote Terminal Unit. Remote Terminal Unit. And PMU stands for Phasor Measurement Unit.
Okay, thank you.
Okay. Any other questions, comments? So I would recommend you all or suggest you all, please once again, after the class is over, you all, I believe you all note down in your notes and once again you think and then I am going to post the answer and then you match with your note and correct and verify it. These are very, very vital, very, very important.
Excuse me, sir.
Yes.
Can you repeat the drawbacks of WAMC, wide area measurement control?
Okay. Because it is related to wide area measurement and control, so it is highly likely that there will be some sort of time delay or communication delay and the cyber attack or cyber hacking issue. So the main drawbacks is that there might be significant time delay or communication delay, as well as high chance of or high possibility of cyber attacks or cyber hacking.
Yes, sir. Thank you.
Okay. Any other questions, comments?
No.
Okay, and then as I said, I'm going to, I myself will write down the answer and then I'm going to post and I will notify you. By the way, so yesterday I sent out an email to you. I have already uploaded homework set 2 and then I think the due date is next week, Tuesday. Did you receive my email yesterday?
Yes, Mr. Ali.
Okay, great. Yeah. So I think there are 5 or 6 questions. So please you all write down and then I have created a Dropbox homework set 2. Please you all upload there by the deadline. I think that is April 14th. You still have 1 week.
Sir, what should be the size of answer? Like,
the answer would not be too long. Just explain means the way we are discussing today. I mean, yeah, answer should be just you have to be very specific and very reasonable. You have to be up to the point. If you need to draw any diagram, so you are welcome to do that. Yeah. Or if you think only text is fine, then do that. I mean, from your side, whatever appropriate you think you do, and then I will be discussing, I will be posting the answers, so you'll be fine. So hopefully next class, there are 2 presentations and I hope I can share you your midterm exam 2 grade. and then I'll be discussing the answers to those questions. And then again, like sometimes next week, again, I'll be discussing some other stuff like HVDC system, cyber security issue system, and then hybrid electric vehicle system, demand side management. And there are still some important thing that I'll be discussing, followed by, this type of question. So I will be creating some question bank for you, and then I'll be discussing. So is there any last minute question comments from anybody?
Good.
Okay, so if no, then thank you everybody, and then so have a good day and be safe. So see you on Thursday. So now I am.
All right, Dr. Ali, see you.
Yes. Okay, now I came back to the camera mode. Can you see me? Okay, so now I.
So we can't see you, Dr. Ali.
So I stop.